Welcome to the deep dive. Today, we're digging into some really foundational stuff for aircraft maintenance. We're taking a look at materials covering aerodynamics, assembly, and rigging.
That's right. And we're aiming this squarely at you, the aviation maintenance technician student, especially if you're knee-deep in your power plant course right now.
Yeah, because you think power plant, you think engine, right?
Right.
Turbines, pistons, fuel.
Exactly. But that engine, it's not working in a bubble. It's creating force that has to work with the airframe in the atmosphere. And if that airframe isn't assembled or rigged just right,
Or if you don't get how the air itself is behaving that day.
then all that engine power might be wasted. Or worse, it could actually be dangerous.
So that's our mission today. We want to cut through some of the, let's be honest, dense textbook language and really connect the dots. How do the laws of flight, the physics, directly impact what you do with your hands, the assembly, the rigging?
We're talking about the non-negotiable procedures, not just theories. These are the laws we work under, and how the condition of that airframe feeds right back into engine performance.
We're looking for those practical takeaways, the stuff that turns knowing the rules into doing the job perfectly every single time.
Okay, let's start with the big one you can't see, aerodynamics. Basically, it's the study of how gases, specifically air, move around objects, like an aircraft.
It's all about how that moving object interacts with the atmosphere. And air, well, it acts like a fluid, right? Mostly nitrogen and oxygen.
Yep, it's a fluid. And it's funny how much of our flight vocabulary comes from the sea.
Oh yeah, like rudder, keel beam. Sometimes you even hear old-timers call the fuselage the hull.
Exactly. But for us as mechanics, the really big difference between air and water, air is compressible, water pretty much isn't.
Okay, compressibility. Why is that specific property so crucial for someone focused on the power plant, on the engine itself?
Because fundamentally, what's an engine doing? It's pulling air in, compressing it, mixing it with fuel. It's an air processor. You absolutely have to understand the stuff you're processing.
Makes sense. So you start with atmospheric pressure.
Right. Which is really just the weight of all the air stacked up above you, that column of air pushing down.
And the standard number we always hear is 14.7 psi at sea level.
That's the one, pounds per square inch. Or, if you're using a barometer, it's about 29.92 inches of mercury, Hg.
Okay, and here's where it directly impacts the engine, especially for you power plant students. Aircraft goes up.
Three big things drop. Pressure, the amount of oxygen available, and the temperature. All go down.
We know that means less lift because the air's thinner. But how does it choke the engine specifically?
Well, it's kind of a double hit. Your engine, particularly if it's naturally aspirated, no turbo or supercharger, is designed to swallow a certain mass of air for the right fuel-air mix.
Right.
So when the pressure drops way off at altitude, even though the volume might seem okay, the actual mass of air going into the cylinders is way down.
Which means less power.
Directly less horsepower. You can have the throttle wide open, but the engine just isn't getting enough air, enough oxygen to make its rated power. It's basically gasping.
So that leads us straight into density, which feels like the thing a mechanic needs to grasp for performance issues.
Oh, absolutely. Density is king. And the rule is simple. Density goes up with pressure, but it goes down with temperature.
Meaning hot air is less dense, high altitude air is less dense. Put them together.
That's your hot and high scenario. Worst possible conditions for performance, high altitude airfield on a scorching summer day, terrible air for making power and for making lift.
So how does this play out when you're troubleshooting, say, an engine that just isn't performing on takeoff?
It's often the first place you look, especially if the engine checks out mechanically. You calculate the density altitude. If it's really high, meaning the air is acting like it's much higher up than it actually is, that explains a lot.
The engine's pulling in less air mass, so less power. The wings are generating less lift, too.
Exactly. Now, here's a weird thing. The plane might actually accelerate a bit faster down the runway initially because there's less air resistance, but it needs way more runway to actually get airborne because it takes longer to build up enough lift. You absolutely have to check the performance charts for that density altitude. Can it actually take off safely in the available distance?
And then there's humidity.
Yeah.
This one still feels counterintuitive sometimes. You think damp air, heavy air.
I know, right? But it's the opposite. Water vapor molecules, H2O, are actually lighter than the nitrogen N2 and oxygen O2 molecules that make up most of dry air.
Significantly lighter, you mentioned.
Yeah, roughly 5/8 the weight. So if you replace some of those heavier N2 and O2 molecules with lighter H2O molecule.
The overall density of the air goes down.
Precisely. High humidity equals lower air density. And again, this isn't some minor academic point.
No, this is runway length stuff.
Yep, absolutely. A heavily loaded plane on a hot, humid day needs a lot more runway than on a cool, dry day. Less lift from the wings, less mass flow through the engine. You absolutely have to factor humidity into your performance calculations or pre-flight checks. Can't just rely on the dry air numbers.
Okay, so we've got the air, it's pressure, temperature, humidity, density, and how that affects engine power. Now, let's nail down how that power actually becomes motion. Back to basics. Newton's laws.
The laws of flight, really. Can't argue with Newton. First law, inertia. An object at rest stays at rest. Object in motion stays in motion unless a force acts on it.
So you need thrust to get moving or change speed?
Yep. Second law, ESMA. Force equals mass times acceleration. The thrust from your engine makes the mass of the aircraft accelerate. More thrust than drag, you speed up. More length than weight, you climb.
Simple but profound. And the third law, action-reaction. This is the heart of propulsion.
Totally. For every action, there's an equal and opposite reaction. How does this work differently for a jet versus a propeller plane?
Well, a jet engine, basically it throws a huge mass of air backwards at really high speed. The reaction, the plane gets shoved forward.
Pure action-reaction. Textbook third law.
Now, a propeller.
It's different. A propeller blade is essentially a wing, an airfoil, just spinning around.
Exactly. It's a rotating airfoil. It generates lift, but instead of lifting the plane up, that lift acts horizontally, pulling the aircraft forward through the air. That's its thrust.
So, for that smooth, straight and level flight, no acceleration, everything's in balance. Lift equals weight, thrust equals drag.
That's the ideal state. And here's where maintenance comes in directly. Let's say you, as the mechanic, you do a repair, maybe replace a cowling, but it's not quite flush. It creates extra turbulence, extra drag.
Then the pilot needs more thrust just to stay level.
Right, which means burning more fuel, putting more strain on the engine, maybe even pushing it closer to its limits. See, it's all connected. Aerodynamics, power plant, maintenance, they all tie together. Okay, let's move from those invisible forces to the actual surfaces that control the aircraft. Airfoils, wings. And the magic behind them is mostly Bernoulli's principle, right? Faster fluid, lower pressure.
That's the core of it. Daniel Bernoulli figured that out. The top surface of most wings is curved, cambered.
So the air going over the top has to travel further, faster than the air going underneath.
Exactly. Faster air on top means lower pressure up there. Higher pressure underneath pushes up, and that pressure difference creates lift.
And it's mostly the low pressure on top doing the work, like 75%.
Yeah, the sources generally agree on that figure. Roughly 3/4 of the lift comes from that low pressure section on top. The other quarter is from the impact pressure underneath.
And pilots can change lift by changing the angle of attack, the AOA. Right. Tilting the wing into the wind more.
Yep, increasing AOA increases lift, up to a point. You can also increase lift by adding wing area, like extending flaps, increasing speed, flying in denser air, or changing the airfoil shape itself, again with flaps or slats.
But push that AOA too far.
And the airflow separates from the top surface, it gets turbulent, stalls, lift disappears quickly. That's the critical angle, the stall angle. Very dangerous.
So to control all this, we have the primary flight controls.
Right. 3 axes of movement. Ailerons control roll around the longitudinal axis, nose to tail.
Elevators control pitch, nose up, nose down, around the lateral axis, wingtip to wingtip.
And the rudder controls yaw, nose left, nose right, around the vertical axis.
Simple enough. But then you get into secondary controls, the trim systems. These seem like a big deal for mechanics.
Well, they are. Because pilots can't sit there pushing or pulling the controls constantly to keep the plane flying straight and level, especially on long flights. Trim tabs are small airfoils on the trailing edge of the main control surfaces.
And they basically hold the control surface in place for the pilot.
Exactly. You've got trim tabs proper, which move opposite to the main surface to correct an out-of-trim condition. Then servo tabs, which actually help the pilot move a large, heavy control surface. And balance tabs, which also move opposite to help streamline the forces. They all need precise rigging.
The systems driving these have evolved massively too, started with just cables and pulleys.
Then hydromechanical systems became common. Still cables and push rods maybe, but with hydraulic boost. The problem there was the pilot often lost the feel of the aerodynamic forces.
So they had to add artificial feel systems back in, springs and bungee cords and things.
Pretty much. Or even stick shakers to literally vibrate the controls to warn the pilot they were approaching a stall because they couldn't feel it naturally anymore.
And now the modern standard is fly-by-wire, FBW.
Completely different world. Pilot moves the stick or pedals, but that input goes to a computer as an electrical signal.
No direct mechanical link anymore.
Nope. The computer interprets the pilot's command, checks it against flight parameters, and then tells electrical actuators out on the control surfaces what to do.
The maintenance impact there must be huge for you AMT students.
Massive. You're not spending as much time with tension meters and turnbuckles on the primary controls, though rigging is still critical for many components. But now you're dealing with wiring, sensors, computer modules, software updates, diagnostic tools.
And redundancy becomes key, right? Multiple computers, multiple signal paths.
Absolutely essential. Triple, even quadruple redundancy is common. Because if that single electrical path fails in an old cable system, you might still have some control. If the computer or power fails in a pure FBW system, well, you need backups. Lots of them. Your troubleshooting shifts from mechanical wear to figuring out if a sensor is lying or if there's a glitch in the code.
Okay, but let's get back to the hands-on skills that are still vital, especially on slightly older or smaller aircraft. Cable rigging?
Still a core skill. You need to know your cables. The most common ones you'll work with are 7x19 and 7x7.
7x19. That's 7 strands, each made of 19 wires.
Exactly. Makes it very flexible. That's what you use for primary flight controls that have to go around pulleys, sometimes tight bends.
And 7x7. Less flexible.
Medium flexibility, 7 strands, 7 wires each. Good for things like trim controls, engine controls where you don't have as many sharp bends. Still needs careful handling.
The ends are critical. The terminations. How do we make sure they hold?
2 main ways you'll see that are proved. First is the nickel press process. It uses special copper sleeves that you crimp onto the cable end using a specific tool.
Patented process, right? Right tool, right sleeves, follow the instructions exactly.
To the letter. If you don't get that crimp exactly right, you won't achieve the full strength of the cable itself. Very important.
And the other method, swaging.
Right, swage-type terminals. These are fittings, usually steel, made to AN or MS standards. You insert the cable, then use a powerful swaging tool, often hydraulic, to basically crush or form the terminal material down onto the cable strands.
And checking that is super critical, the go, no-go gauges.
Absolutely non-negotiable. After swaging, you use these precise gauges to measure the diameter of the terminal shank where it was compressed. If it's too small, over-swaged, or too large, under-swaged, the connection is weak. It won't hold the rated load.
How weak are we talking?
It can be drastic. Being off by even a small amount on that swage diameter can cut the cable's braking strength in half or more. Imagine a control cable snapping during a routine maneuver.
Catastrophic. And you mentioned something about soldering. Big no-no.
Huge no-no. Never, ever solder the ends of control cables, especially near a swage or nickel press fitting. The heat affects the wire temper, and the solder itself can actually wick into the strands and make it more likely for the cable to pull out under load. Just don't do it.
Okay, swaging done right, termination secure. Now, the big headache, setting the tension, especially with temperature changes.
Yeah, this is where physics really bites you. The aircraft structure, mostly aluminum alloy, expands quite a bit when it gets hot and shrinks when it gets cold.
High coefficient of thermal expansion.
Right. But the control cables are typically steel. Steel still expands and contracts, but way, way less than aluminum.
So you rig a cable nice and tight in a cool hangar in the morning?
Then the plane sits out on the sunny ramp all day. The aluminum fuselage gets longer. Your nice, tight steel cable, now it's relatively loose, could even be slack.
Leads to sloppy controls, delayed response.
Exactly. Or the opposite. You rig it on a really hot afternoon. Plane flies up to altitude where it's freezing cold. The aluminum structure shrinks significantly.
And now that steel cable is banjo string tight.
Dangerously tight. It could bind the controls, put huge stress on pulleys and bearings, even cause structural damage over time.
Which brings us to the absolute necessity of the cable rigging chart. The tensiometer alone isn't enough.
Not even close. The tensiometer is great, tells you the tension right now, maybe 98% accurate, but that's not the whole story.
I need the chart.
You must use the chart provided in the maintenance manual. It tells you. Okay, the outside air temperature right now is 75 degrees Fahrenheit. For this specific size cable, say 18-inch 7x19, you need to set the tension to X pounds using your tensiometer.
And that X pounds accounts for the expected expansion or contraction when the aircraft is actually flying at temperature extremes.
Precisely. You're setting the tension on the ground so that it will be correct under flight conditions,
Yeah.
ignoring that chart. That's asking for trouble. It's fundamental.
Okay, and the hardware we use for this adjustment, turnbuckles.
The standard way to fine-tune cable length and tension. It's a barrel with threads inside. One end takes a cable terminal with right-hand threads.
And the other end takes a terminal with left-hand threads. So turning the barrel pulls both ends in or pushes them out simultaneously.
Right, and you can usually tell the left-hand thread end because the terminal or the barrel itself will have a groove or knurling on it. Little visual cue.
Critical installation point.
Yeah.
Thread engagement.
Huge. You have to make sure both terminals are screwed into the barrel roughly equally, and most importantly, the manual will specify. No more than 3 threads should be exposed on either terminal shank outside the barrel.
If you see more than 3 threads showing.
It means there isn't enough thread engagement inside the barrel. The connection is weak. It could pull out under load. You need a longer or shorter push rod or maybe even a different length cable assembly.
And once it's set, tensioned correctly, threads checked. Safety wire.
Absolutely mandatory. Double wrap safety wire, usually using the double twist method with stainless steel wire like 0.032 inch. Secure that turnbuckle barrel so vibration can't possibly make it turn and change the tension.
All right, let's completely switch gears now.
Mm-hmm.
Forget fixed wings for a moment. Helicopters, rotorcraft. The dynamics here are, well, complex.
That's putting it mildly. Instead of a wing moving forward through the air, you've got this massive airfoil, the main rotor, spinning around. It generates lift, yes, but it introduces a whole bunch of other forces you have to manage.
Starting with torque, Newton's third law again, biting us.
Right back at you. The engine works hard to spin that heavy main rotor system in one direction.
And the reaction is the fuselage wanting to spin the other way, violently, if you don't counteract it.
Exactly. The more power you pour into the main rotor, the stronger that torque reaction gets.
So in most single-rotor helicopters, that's the job of the tail rotor.
Primarily, yes. It's basically a small propeller mounted vertically, pushing sideways to counteract the main rotor torque, and also providing yaw control.
But there are other ways, too, like the fenestron.
Yep, the fenestron is essentially a ducted fan in the tail boom, more protected, quieter sometimes. And then there's the really clever no-tar system.
No tail rotor. How does that work?
It uses low-pressure air from a fan inside the fuselage, ducted down the tail boom. Some air exits through controllable slots along the boom, creating a boundary layer control effect, Coanda effect, that generates side force. And then a direct jet thruster at the very end gives yaw control. Pretty ingenious.
Okay, back to the power plant focus. How does engine management differ in a helicopter compared to a fixed wing?
Yeah.
RPM seems way more critical.
Oh, it's paramount. Main rotor OPM has to stay within a very narrow band for aerodynamic efficiency and stability. In turbine helicopters, it's usually managed automatically by a governor.
The governor senses RPM changes and adjusts fuel flow to keep it constant.
Pretty much. Pilot changes the collective pitch, which changes blade angle and thus drag lift. The governor senses the RPM droop or rise and instantly adjusts fuel to compensate, holding that RPM steady. It's quite sophisticated.
Piston helicopters sound trickier. You mentioned a correlator.
They are a bit more hands-on. The pilot has direct control over the collective pitch lever, changes angle of all blades together for up-down movement, and the throttle controls engine RPM. But they're linked. Increasing collective pitch adds a lot of drag, which naturally slows the rotor RPM down. Decreasing it does the opposite. The correlator is a mechanical linkage between the collector and the throttle. As the pilot raises the collective, the correlator automatically opens the throttle a bit to anticipate the droop.
Just a rough adjustment, though.
Yeah, it gets it in the ballpark. The pilot still has to fine-tune the throttle manually to keep the RPM precisely where it needs to be. And here's the tricky part for rigging. In a piston helo, the collective is your primary control for manifold pressure, engine power, but it's also a secondary control for RPM because of the drag change.
And the throttle is primary for RPM.
But secondary for manifold pressure because changing RPM changes how much air the engine pumps. So when you're rigging those controls, that mechanical correlation has to be absolutely perfect so the pilot's inputs result in synchronized, predictable changes to both power and RPM. It's delicate.
Wow. Okay, now the really mind-bending physics of the rotor disc itself. Gyroscopic precession.
Ah, yes. Fun times. Any spinning object, like a bicycle wheel or a main rotor, acts like a gyroscope. It has stability, but it also does weird things when you apply force.
Like precession. You push on one point.
And the maximum effect, the maximum deflection, doesn't happen there. It happens about 90 degrees later in the direction of rotation.
90 degrees later.
Yep.
So if the pilot wants the rotor disc to tilt forward, to fly faster?
They push the cyclic stick forward, but the mechanical linkages in the swash plate, we'll get to that, are rigged so that this input actually causes the maximum downward pitch change on the blade when it's passing the pilot's left side, assuming counterclockwise rotation.
So that by the time that blade reaches the front, 90 degrees later, it's at its lowest point, tilting the whole disc forward.
Exactly. The rigging has to anticipate and account for that inherent 90-degree lag. If you rigged it so the force applied directly forward, the helicopter would tilt 90 degrees to the right. Not ideal.
Understatement. Okay, next headache. Dissymmetry of lift.
Right. This happens only in forward flight. Picture the helicopter moving forward. The rotor blade that's currently swinging forward, the advancing blade, feels the airspeed from rotation plus the helicopter's forward speed.
So it's moving through the air really fast, lots of lift.
Huge lift. But the blade on the other side, swinging backward, the retreating blade, feels the rotational speed minus the helicopter's forward speed.
Much slower relative wind, much less lift.
Exactly. If you didn't correct for this, the advancing side would generate vastly more lift than the retreating side, and the helicopter would instantly roll over, catastrophically.
So how does the rotor system fix this automatically, flapping and feathering?
Yep. Most rotor systems have hinges allowing the blades to flap up and down independently to some degree. As that advancing blade generates all that extra lift, the lift itself forces the blade to flap upwards.
And flapping upwards changes its angle of attack.
It effectively reduces the angle of attack, which reduces its lift. The opposite happens on the retreating side. Less lift causes it to flap down slightly, increasing its AOA and generating more lift. It's a self-balancing act. Plus, the pilot's cyclic inputs also feather the blades, change their pitch angle individually, throughout the rotation cycle to fine-tune this balance.
Amazing engineering. Then there are efficiency effects, like translational lift.
Right. When a helicopter is hovering, it's sitting in its own downwash, these turbulent vortices of air it's pushing down. Not very efficient.
But as it starts to move forward,
It starts to outrun that messy recirculating air. The rotor starts flying into relatively undisturbed air. This increases efficiency.
and ETL, effective translational lift.
That's the point. Usually around 16 to 24 knots of forward speed, where the rotor completely outruns its own vortices. You get a noticeable bump in efficiency and performance. The helicopter feels like it wants to climb or accelerate without adding more power. Pilots plan for this.
And ground effect. That's about hovering close to the surface.
Exactly. When you hover very close to the ground, typically less than 1 rotor diameter altitude, the ground itself physically restricts the formation of those big wingtip, blade tip vortices.
Less vortex means less induced drag.
Precisely. Less drag means the rotor system is more efficient. It takes less engine power to hover in ground effect, IGE, than it does to hover higher up out of ground effect, OGE. This difference is critical for calculating lifting capability, especially at high altitudes or temperatures.
Okay, maintenance focus. What's the #1 rigging task for a helicopter mechanic?
Without a doubt. Blade tracking. Making sure all the main rotor blade tips are flying in the exact same plane, following the same path through the air, within incredibly tight tolerances.
Why is that so critical? Vibration.
Massive vibration if they're not tracking together. One blade flying slightly higher or lower than the others introduces a 1 per revolution vibration that shakes the whole aircraft, causes discomfort, and leads to premature wear and tear on everything.
How do you check it? The old way sounds interesting. Flag and pole.
Yeah, the old school method. You'd literally have someone hold a pole with a piece of canvas near the rotor tips, maybe with different colored chalk applied to each tip. You'd spin up the rotor carefully, let the tips mark the canvas, shut down, and see if the marks lined up.
Labor intensive and maybe not super precise.
Exactly. Functional, but time-consuming and prone to error. Today, we use electronic blade trackers. Systems like the Strobex or Vibrex.
How do those work? Strobe lights.
Yep. They use a strobe light that flashes precisely in sync with the main rotor's rotation. This makes the blades appear stationary when they're spinning. Each blade tip has a reflective marker or number on it.
So you can just look and see if they're all lined up perfectly.
Pretty much. You look through the tracker, see the frozen blade tips, and you can measure any difference in their vertical position very accurately. Then you make tiny adjustments to the pitch links connecting the blades to the swash plate until they all track within the manual specified limits, often just fractions of an inch.
Speaking of the swash plate, that sounds like the heart of the control system.
It really is. The swash plate assembly is this amazing piece of engineering that translates the pilot's stationary control inputs into commands for the rotating blades.
It has 2 parts, stationary and rotating.
Correct. A non-rotating lower swash plate is connected via linkages to the cyclic and collective controls in the cockpit. It can tilt in any direction and move up and down.
And the upper part.
The upper swash plate is mounted on a bearing on top of the stationary one, so it can rotate with the main rotor mast. It's connected by pitch links, adjustable rods, out to each individual blade grip.
So pilot moves the cyclic, the stationary plate tilts.
That tilt is transferred through the bearing to the rotating plate, which then, through the pitch links, changes the pitch angle of each blade individually as it goes around its cycle, creating that tilt in the rotor disc we talked about for precession.
And collective input just raises or lowers the whole assembly together.
Raises or lowers both plates together, which changes the pitch of all blades equally for climb or descent. Rigging that swash plate, the linkages, the pitch links, it requires absolute precision, following the manual to the thousandth of an inch sometimes.
It sounds like rigging a helicopter is just next level compared to fixed wing.
It demands extreme patience, meticulous attention to detail, and slavish adherence to the manufacturer's maintenance manual. Every clearance, every tolerance, every sequence matters. And it always ends with thorough functional checks, confirming control movements, pitch angles, and finally, that crucial blade track. So whether you're working on a simple fixed wing or a complex helicopter, one thing is constant. You live and die by the documentation.
And these aren't suggestions, right? They're the law.
Absolutely. Your primary source of truth, the highest authority, is the Type Certificate Data Sheet, the TCDS for that specific aircraft model.
That's the FAA's official description. What's in it?
Everything fundamental. Certified limitations, airspeeds, weights, center of gravity range, engine and prop models approved, control surface movement limits. If it's not in the TCDS or reference materials, you can't do it or install it legally.
Okay. Below the TCDS.
You've got the aircraft maintenance manual that tells you how to do the work, the procedures, the tolerances, the required inspections. Then there's the structural repair manual, SRM, for guidance on fixing common structural damage.
And service bulletins or letters.
Right, service information. That's how manufacturers communicate required modifications, improvements, or urgent safety information. You absolutely have to stay current with those. Following the approved data is paramount for every single task.
Let's talk about a procedure that perfectly blends aerodynamics, structure, and maintenance. Control surface balancing.
Yes, crucial stuff. Anytime you do anything that changes the weight or weight distribution of a control surface, like a repair, adding paint, even if moisture gets trapped inside, you have to check its balance.
Why is this so critical? It feels like we're talking about tiny amounts of weight sometimes. Ounces.
It might seem small, but it's about stability and preventing a catastrophic phenomenon called flutter.
Oh, flutter. That sounds bad.
It's horrifying. Flutter is a self-excited, rapidly escalating oscillation, a violent shaking of a control surface that can occur at higher airspeeds. It happens when the aerodynamic forces, the inertial forces of the surface's mass, and the structural stiffness all interact in just the wrong way.
And an unbalanced surface is more prone to it, especially trailing edge heavy.
Exactly. A surface that's heavy behind the hinge line, static under balance, is inherently unstable. It wants to diverge, to flap wildly. If flutter starts, it can literally tear the control surface or even the whole wing or tail off the aircraft in seconds.
Seconds. Wow. So we need to make sure they're balanced correctly, maybe even slightly nose heavy.
Precisely. The goal is usually a slight static overbalance, meaning the surface is balanced slightly ahead of the hinge line. This nose-heavy tendency makes it inherently stable and resistant to flutter.
How do we actually check and achieve this balance as mechanics?
Several ways. For very minor changes, like maybe just touch-up paint, you might use the calculation method. You figure out the weight you added or removed, measure how far it is from the hinge line, calculate the moment, weight times distance, usually in inch-pounds, and see if it's still within limits or requires adding or moving counterweight.
Okay, for bigger repairs.
You'll likely need to remove the control surface from the aircraft. Then you might use the scale method, placing the surface on special knife-edge fixtures or jigs that are positioned right at the hinge line, and using sensitive scales to measure the actual weight distribution.
Or the balance beam method.
Yeah, some manufacturers, like Cessna and Piper, specify using a dedicated balance beam tool. Again, requires removing the surface, but it gives a direct reading of the balance condition relative to the manufacturer's required datum.
And if it's out of balance, we add or remove counterweights, usually located in the leading edge.
Correct. These counterweights are often made of lead or steel because they're dense, but sometimes, especially on larger or faster aircraft where space is tight,
They use something even denser, depleted uranium.
that's right. Depleted uranium, DU, is extremely dense, much denser than lead, so you can get the required counterweight mass into a smaller physical space.
Okay, safety brief time. Depleted uranium sounds concerning.
It requires specific handling precautions, absolutely. DU is primarily an alpha emitter, which means the radiation risk is mainly internal if you inhale or ingest dust particles.
So grinding or drilling on a DU counterweight is a bad idea without protection.
Extremely bad. The maintenance manual will have very specific procedures. You need proper PPE gloves, respirator, good ventilation, careful cleanup. You treat it with respect, follow the procedures, and the risk is managed. But you must know if you're working with it and follow the safety rules precisely.
Got it. Okay, before we even touch control rigging or balancing, the whole aircraft needs to be sitting correctly, right? Leveling.
Foundational step. If the aircraft isn't properly leveled, all your subsequent measurements for rigging will be skewed. On small planes, it might be as simple as placing a spirit level across specified points on the fuselage frame or door sills.
Larger aircraft. More complex.
Usually involves using plumb bobs hanging from specified points over a grid plate on the floor, or using specialized leveling jacks and transit levels. You need to ensure it's level both longitudinally, nose to tail, and laterally, wingtip to wingtip. This also allows you to check crucial structural alignment aspects like wing dihedral, the upward angle of the wings, and incidence, the angle the wing chord makes with the fuselage centerline.
Only then can you start rigging controls accurately.
Only then. And you circle back to cable tension using that tensiometer and the temperature compensation chart we stressed earlier.
Setting the tension for flight conditions based on the hangar temperature.
Got it. Then you set the control surface travel limits, making sure the control moves through its full required arc, but no further.
How do you verify that? Protractors.
Often, yes, using large protractors or special rigging templates and fixtures provided by the manufacturer. You measure the deflection in degrees, up and down, left and right, ensuring it matches the TCDS limits precisely. The cockpit control also needs to hit its stops at the same time the surface hits its stops, no binding or over travel.
Okay, everything's rigged, tensioned, travel set. The final step before signing off.
Safetying. Got to make sure nothing can vibrate loose. Nuts, bolts, turnbuckles, anything critical.
And the gold standard for that is safety wire. Double twist.
For critical components, yes. Usually 0.032-inch stainless steel wire installed using the double twist method. It provides positive locking. 2 wires twisted together, threaded through the bolt head or nut, and anchored securely. Takes practice to do neatly and correctly.
But you mentioned a single wire method, too. For different things.
Right. Important distinction. For things like emergency equipment seals, fire extinguishers, first aid kits, things like that, you might use a single strand of softer wire, like copper or aluminum. This isn't meant to hold tight against vibration.
It's a tamper seal.
Exactly. It's designed to be easily breakable by hand. If that wire is broken, you know someone has potentially used or tampered with the equipment, even if a gauge looks okay. Different purpose, different method. And after all, rigging. A mandatory inspection by a second qualified person is always required. #tag outro.
So wrapping this all up, I think this deep dive really shows that being a top-notch AMT, especially on the power plant side, means you have to be fluent in physics, not just turning wrenches.
Yeah, it's not just about the engine in isolation. That poor engine performance you're troubleshooting. It might not be the fuel control unit at all.
It could easily be high-density altitudes starving it for air, or maybe improperly rigged flight controls creating so much drag that the engine just can't keep up. You have to see the whole system.
Absolutely. The aircraft's safety, its performance, it all hinges on these fundamental physics principles. Aerodynamics, forces, balance being meticulously maintained by you, the technician. Every time you use that tensiometer correctly, every time you check a swage with a gauge, every time you balance a control surface, you're literally upholding the laws of flight. It's a huge responsibility.
Okay, so here's our final thought. Something for you to chew on as you continue your studies and head towards certification.
We've spent a lot of time talking about the incredible precision needed for traditional mechanical rigging, measuring threads on a turnbuckle, compensating for aluminum expansion, meticulously tracking rotor blades. It's very hands-on, very physical.
But we also touched on fly-by-wire, stability augmentation systems, the move towards software-driven flight controls. Stability in these newer aircraft relies more and more on sensors sending data to computers running complex code rather than purely on mechanical alignment and inherent aerodynamic stability.
So the question is, as this transition accelerates, how does the required expertise of the AMT shift, especially for those of you specializing in power plant and the associated control systems? If ensuring stability becomes more about diagnosing faulty sensors or corrupted software than about physically aligning cables and rods, what does that mean for your skill set?
How do you prepare for that future where mechanical precision might share the stage, or even take a back seat to electronic and software diagnostic skills? Something to think about.